This section is 15.4, and we're going to cover here air columns, just like we covered strings in the last section. Now, air columns consist of an opening at one end, both ends closed, or both ends opened. Now, what must we have in these various cases where we have both ends closed, both ends open, or say one end opened and one end closed? It turns out that an air column that has a closure must have a node there. If it has an opening, it must have an antinode. And we can look at these and say, how do they behave? Well, if it's closed, then I must have exactly a node at each end. Therefore, this is going to be exactly like our situation with strings. I must have, in order to get a node at each end, a half a wave, half a wave, half a wave, I must have an integer number of half waves in the length of the object. Now, if it's open at both ends, then if I think about a wave, if I go from let's say here's a wave, and rather than looking at the node, if I look at the antinode, if I must have an antinode at each end, then I must have a half of a wave, or a half of a wave, or back to a half of a wave again. And so if you think about it, a half of a wave must exist here to have an antinode at each end. So if it's open at both ends, a column will be the same kind of formula. Consequently, if a column of air is closed at both ends or open at both ends, the vibrations that can exist inside are both the same. And this gives us, of course, that the wavelength must be equal to twice the length over an integer. And therefore, the frequency, as we derived last time, must be equal to n times v over 2L, or equivalently, the nth frequency must be n times the first frequency. So we get exactly the same equation. This is closed at both ends, closed at both, open at both. This will give us our equation, and it's the same as strings. So a string is like an air column that's actually closed at both ends, forcing a node. Now let's look at the situation where we have an air column that's open at one end and closed at one end. Then in this case, it must have a node here and an antinode here. Well, this requires a lot more thought. Let's imagine that we start out with our wave. We'll draw several parts of this wave now. And here we have a closure. And now the end could be here at an antinode, or here, or here, or here. How do we characterize that? So it can be, this is actually, turns out to be a fourth of a wave. So we could have, if this is the length here, we could have it where a wavelength over a 4 was equal to the length of the air column. So it'd start out here with a node, have an antinode here, or I could have 3/4, 3 lambda over 4 could equal my length. Or if I look at here, that could be the opening, because it's an antinode, remember. This would be a whole wave plus another fourth, so that's 5/4. Now you begin to see the pattern. I can have an integer over 4 times the wavelength if that integer is odd. So for open at one end and closed at one end, like a Coke bottle that you blow across, I have an integer that's odd divided by 4 times the wavelength is equal to the length. And that gives me an equation which says that the frequency is going to be equal to the velocity over the wavelength, which is n odd v over 4L. Now, if I take that and look at this v over 4L, that's the first one. And so in general, we can say the frequency of the nth one is an odd integer times the first. So it turns out that if the column is closed at one end and open at the other, I get all of the odd harmonics, but not the even harmonics, which I get in the other circumstances. Now, again, let me mention that this first harmonic is called the fundamental. N is equal to 1. It's called the fundamental. That's the fundamental frequency that we're going to have. And the nth one of these oscillations is going to be called the nth harmonic. So this is the fundamental, is the first harmonic. N equals 1 is called the fundamental. It's also called the first harmonic. N equals 2 is called the second harmonic. And so forth. N equals 3, third harmonic. Now, there's another name for these. In addition to the fundamental, this is also called, this N equals 2, the first overtone, because it's a tone over that first harmonic. This is called the second overtone. Sorry, my paper got off there. So N equals 1 is the fundamental, first harmonic. N equals 2 is the second harmonic. N equals 3 is the third harmonic. The first harmonic is the fundamental, but the second harmonic is also called the first overtone, second overtone, and so forth. And so we have two equations. This one, which applies to strings, columns that are open at both ends, closed at both ends. So three different circumstances describe that one. But if a column of air is open at one and closed at the other, we have this equation here, or something like a Coke bottle. And this is the way we name these fundamental frequencies for both air columns and for strings. We can see then that the fifth harmonic is the fourth overtone. The first harmonic is also the fundamental.